Hello. So today we're going to look at a short theorem from Introduction to Number Theory. I got this theorem from the start of the textbook Algebra by Thomas W. Hungerford. So we have n integers such that one of them is non-zero. We're going to define the GCD of these integers to be a positive integer c such that this condition 1 holds, which states that c is a common divisor of all of the AI. And secondly, for any other common divisor, um, um, the common divisor is also a divisor of the GCD. Okay, so that's condition 2. The theorem that we're going to state and prove today is that under the above assumptions, in particular, one of these integers, j, is non-zero, at least one of them is non-zero, then the GCD exists. And furthermore, we can find n integers such that the GCD is a linear combination of the AIs with coefficients given by these integers k1 through kn. Okay, so the proof is as follows. Okay, so just zoom out a little bit here. Okay, so the start of the proof, we're going to define the set S to be the set of all linear combinations with coefficients in the integers, linear combinations of these fixed a1 through an, such that the linear combination is positive. Okay, so S is the set of all positive linear combinations of the AIs. Now, this set is non-empty since we've assumed here that that one of the AJs is non-zero. So, for instance, we could just take all of the xi's to be 0 except for xj, and then set xj equal to plus or minus 1, depending on the sign of aj. Okay, so since S is non-empty, and it's a subset of the natural numbers here, so it only contains positive numbers, then it must have a minimal element. So we're going to call this minimal element C. Now we're going to show that this minimal element C satisfies properties 1 and 2 of the GCD. Okay, so the first property is to show that it's a common divisor, okay, of the AIs. So we're going to suppose, for sake of contradiction, that that it doesn't divide one of the AIs. Okay, so then by the division algorithm, we can find two integers, q and r, where r is the remainder, such that this r integer is between 0 and c. Notice it's strictly positive because we're assuming that c does not divide the AI. Okay, so this r is going to be strictly positive. Okay, and right, and so we have such that the AI is equal to c times some integer q plus r. Okay, all right. So if you're not familiar with this process, this is what's called the division algorithm, and so you can look that up on your own time. Okay. Now, since C is a linear combination of the elements of the AIs, we can replace C in this equation with the linear combination itself, and then subtract over this term CQ to the left-hand side. So that's what I've done here, and what that means is we can express R as a linear combination of the AIs, okay? Because C is a linear combination of the AIs by assumption, and this is obviously just this 1 times AI, and so therefore we can express R as a linear combination of the AIs. But that means that R satisfies the condition. Remember, that means that R satisfies the condition to belong in S, because R is a positive linear combination of the AIs. And R is less than C, which is a contradiction because C is supposed to be the minimal element of S. So we've contradicted the minimality of this element C. So there's our contradiction symbol. And therefore, we must have that C is a common divisor of the AIs. All right, and now to prove the second property of the GCD, in particular that that any other common divisor must be a divisor of the GCD, we assume that we have another common divisor, and then it actually follows immediately, because if you have a common divisor of these AIs, since C is a linear combination of the AIs, then this divisor D will just divide every term in this linear combination. And so it's going to divide C. Okay. So this is not my expertise. This field is something I've been self-studying algebra over the summer because it's kind of my weakness. So if there are any holes or flaws in this, please let me know. Have a nice day.